In this chapter, we will be studying antidifferentiation and integration. In this lesson, we will be looking at how to use substitution to help us solve integration problems.
All right, everybody. In this lesson here, we're going to take a look at the substitution rule. Now, up to this point, when we've been doing integrals here, we've been really just doing them as if they were antiderivatives. And by that I mean we were just taking the rules of differentiation and going backwards with them. Okay, and I've been hinting at the existence of a rule that's going to make these questions, or some of these questions that we've been doing, a little bit easier. And here's that rule that I was talking about here. It's called the substitution rule, and I'll show you how it works here. Now, some of you have been doing these antiderivatives or these integrals sort of instinctively, intuitively, and you're seeing the pattern without actually having to do what I'm about to do here, and that's totally fine. But for those of you that maybe require this, there's a little bit of structure that I can give you that'll help you find these antiderivatives or these integrals a little bit easier. So here's what we're going to do here. We're going to let u be the function g of x, okay? And then we're going to, when we take a look at an expression here where it's the integral of f of g of x. Now notice what's going on here. This is a composed function. Okay, f is composed with g, and it's multiplied by the derivative of g. Okay, with respect to, and then we're taking the integral with respect to x here. So again, notice the pattern here. Composed function, we've got the derivative of the inside here. That's going to be simplified down into the integral of f of u du. Yes, I know, I wrote fu in there. Okay, get over it. So let's keep moving on here. Now, to really get a sense of how substitution works, really what we got to do is just get in there and do some examples so that you can see it happen. So that's what I'm going to do here. So I've got a series of examples that we're going to work together on. So this first one right here, we're going to take the integral of 8x cubed multiplied by 1 plus 2x to the fourth all to the 1/2 with respect to x. Okay, so x here is our independent variable. Now, when I see this, I can see the composed function here. Okay, like don't worry about this over here, this 8x cubed. That's fine. But notice that we've got this f of g of x here, that composed function bit here. And what we're going to do normally is let u equal the interior function. So what I'm going to do here is I'm going to replace what's inside here with u. So I'm going to let u equal 1 plus 2x to the fourth. Okay, and what that's going to allow me to do is to replace this little bit in here. Okay, so I'm going to end up writing, this is going to be the integral of u. Now I'm going to give myself some room here. This is going to be an integral of u to the 1/2. That's awesome. That's awesome. Except that, let me zoom in a little bit more here. Except that the integral here was with respect to x, not with respect to u. And I've got the differential of x here, not the differential with respect to u. So although I've made this substitution to u, it's not complete. I need to change the differential to a differential with respect to u. I need to make that complete change. And if you look up into your substitution rule here, yeah, we've got the differential with respect to u. So let's take a look at how we might do that. And actually, it's very easy to do. What I do is I go to this substitution expression that I've got, I take the derivative of it. So this will be du by dx. And notice that when I do that, bring down the 4, I will get 8x cubed. Well, that's just fantastic because notice that is that exterior function here. There is the derivative of g. So now what I'm going to do, and I do this slightly differently than some of the other teachers at school here. What I'm going to do here is I'm going to get dx by itself. I'm going to solve for that differential of x. Now, in my mind, that simplifies the problem a little bit when I solve for dx here. Okay, but I actually can do that. I take the derivative of u with respect to x, and then I'm going to solve for dx so that I can make a substitution. So over here, I still had 8x cubed there. I've got this 1 plus 2x to the fourth all to the 1/2. Well, I replaced that 1 plus 2x to the fourth with u. And now I'm going to replace dx with du over 8x cubed. And I hope you see why I did that, because those those two factors right there are going to cancel. And so we're going to be left with the integral of u to the 1/2 du. Okay? And actually, that is a pretty easy one to work with. All I do is I increase the exponent by 1. So increasing 1/2 by 1 will be u to the 3/2. And then I'm going to divide by 3/2, and I will deal with that in just a second. I'll clean that up a little bit. But I should be hearing people in the class going, what about the plus c? That's right, because I would dock you if you didn't do that. It's important. This right here, okay, this is an indefinite integral. I don't have limits here, so I gotta have that arbitrary constant popping up when I take the integral. Wonderful. So now, this is going to be 2/3 u to the 3/2 plus c. I'm almost done. Okay, I'm not quite done yet because I can't leave this with respect to u. The original question was not asked with respect to u. So I need to go back and make that substitution back in. The u is actually called a dummy variable. Okay, it doesn't become part of the actual work. It shouldn't be left over at the end here. It's if you want to compare it to let's say something in chemistry, it's like a catalyst. It enables me to perform this operation, but it shouldn't be the final answer here. I should go back and make this 2/3. This will be 1 plus 2x to the 4th, all to the 3/2 plus c, and that's the integral that I'm looking for. And you can verify that that's true by taking the derivative of this, and you will see that actually you go right back to that original question there. Okay, let's take a look at another one. Okay, the integral, and again, notice that this is an indefinite integral. Now, they don't have to be indefinite integrals. It's just my first couple of examples are going to look like that. I have got the integral of x over the square root of x squared plus 1. Now, when I look at this, I should see some composition here. Okay, I should see some function composition. And what that is it's the square root of x squared plus 1. That's my composition. So when I make my substitution, when I introduce the variable u, I'm going to let u be the interior function, and that's going to be the x squared plus 1. So when I rewrite this, I'm going to put a u down here under that square root. And that'll be great, except that I need to do more than that because I need to get rid of the differential. If I'm going to introduce the variable u, I want to then change the question so that I'm taking the integral with respect to u. So again, I got to change the differential, and I'm going to keep mentioning that as we go through. Okay, so it's always something you're thinking about. So I need to take the derivative of u, okay, with respect to x. And then what I'm going to do is I'm going to solve for that differential dx there. So this is going to become du over 2x is equal to dx. Good. So now I can take this and substitute it into my original integral here, my question. So this will become the integral of x over root u. And then dx becomes du over 2x. Okay. Good. So now I'm just going to clean that up a little bit. Notice that the x's will cancel here. And that's good. I like that. I'm still left with a 2 in the denominator. But if you remember back to a previous class here, having a coefficient up front, that's not a problem. I'm just going to move that out front. So I'll make that 1/2 the integral of du over root u. Okay, good. It's a much simpler expression. It is just in terms of u, and my integral is telling me to take the integral with respect to u. So that's a big step forward here. Now, I'm going to clean that up just a little bit here and make this the integral, 1/2 the integral of u to the negative 1/2 du. A little bit easier to take the integral when I've got it in exponential form than if it's in radical form. Okay, so now I am going to increase the exponent by 1, and then I'm going to divide. Okay, I'm going to divide by the new exponent here. So this is going to be 1/2, and then out here u to the 1/2 divided by 1/2. Wait for it. Plus c, that's right. Okay, good. Plus c. Always remember to put the plus c when it's an indefinite integral. Okay, so now my 1/2 here will actually cancel, and so I'm going to be left with u to the 1/2 plus c. And again, because the initial question was not asked in terms of u, because originally the independent variable was x, I got to go back and plug in my expression for u. Now that's easy because it's just over here. It's just x squared plus 1. So my final answer over here will be the square root of x squared plus 1 plus c, that arbitrary constant out the back side there. Okay, good. Now, something that you should know about the substitution rule is that sometimes it's hard to know exactly what counts as the interior function, okay, of that composed little bit there. And I'll show you with an example here. Whoops. Okay. So I've got the integral of the natural log of x minus 5 over x minus 5. Now, initially here, it would be totally logical to assume that my composed function here is the natural log of x minus 5. So what I would do here is let u equal x minus 5. Okay, so I'm going to switch my independent variable from x to u, and then I need to introduce the differential, so I take the derivative, and that's just going to be equal to 1. It's kind of convenient. So du is equal to dx when I solve for dx here. So now I'm going to make my substitution up into the original equation here. Okay, and so this would end up being the integral of the natural log of u, okay, over x minus 5. And then I would have this du on the outside here. Well, okay, I'd like to get rid of that x minus 5 there. Well, I know that that's equal to u. Okay, so I can make this the integral of the natural log of u over u du. And now, okay, that doesn't actually get me anywhere, because really all I've been able to do is rewrite this expression without the negative 5 there, but it's basically the same thing. I have gotten nowhere. When you run into a situation like that, that's because your substitution here was incorrect. Okay, or at least in this course here, if you've got a problem that certainly has this look like it's going to require substitution, and if you make that substitution and you get a result that really doesn't lead you closer to the final answer here, or you get to a spot where you're stuck again, okay, well, make a different substitution. And I will show you what the actual substitution that makes this work here in just a second. Something that you should be aware of, though, as well, sometimes you might actually have to make multiple substitutions. So sometimes I'll make a substitution here, get it down to here, and then I'm going to have to do another substitution to get the answer, and then maybe even another one. Okay, that's totally possible. That is not what's going on here, though. What we're going to do here is we're actually going to change what it was that we let u equal to. And if you take a look at the original question here, you actually don't have many other options for what u could be. But let's let u equal the natural log of x minus 5 in this case. Okay, so now when I take the derivative with respect to x, remember that the derivative of the natural log is going to be 1 over the argument multiplied by the derivative of what was inside there, which is just going to be 1 in this case. Now, if I solve for that dx, that differential there, that's going to be x minus 5 du is equal to dx. Okay, now let's go back and look at our expression here. So the original question was the integral of the natural log of x minus 5 over x minus 5 dx. Okay, I've made a substitution here. I have let u equal the natural log of x minus 5, so that is going to be the integral of u over that x minus 5, and now I'm going to replace the dx with x minus 5 du, and I hope that at this point here you're seeing how that's going to work out so nicely for me, because now those x minus 5s are going to cancel. This becomes the integral of u du, which is absolutely brilliant, okay, because that's an easy integral. That's just going to be u squared over 2 plus c. Okay, good. Always got to have the plus c when it's an indefinite integral. And now I just got to go back in and replace the u with that expression that had x as the independent variable. And so now my answer is going to be, now I got to put this in brackets, it's going to be squared over 2 plus c. And u in this case was the natural log of x minus 5. Now, it does look a little funny to write it like that. I mean, that's how you'd have to write it, because if you put the 2 on the x minus 5, it would look like the square is on the argument of the logarithm, and that's not what I want. I want the square to be on the whole logarithm. Another thing that you might do here is make this the natural log squared of x minus 5 over 2 plus c. Okay, that should sort of remind you of what it looks like when we do trigonometry and we're squaring, for example, like a sine or a cosine function. Okay? All right. Let's keep going. Let's take a look at another one. Okay, this time, notice that this question, this one here is a definite integral. I've got limits here. Now, I bring this one up here because I'm going to show you a couple of things that you can do with this. Okay, because there are, once you've got a definite integral, there are a couple of things, a couple of ways that you can go about approaching this. And I'll show you two of them here. Actually, what I'll do here is I'll do this one in one way, and I'll do the next one in the other, using the other method here. Okay, so when I take a look at this, again, I'm looking for a function of a function. I'm looking for that composition. And I'm just looking at my denominator here. That's where I'm seeing the function of a function. I'm seeing the cube of the sine. So I'm going to let u equal the sine of theta. It's probably not a big jump here to see why that would be a good choice there, because as soon as you take the derivative of that, you're gonna spit out that cosine there. So here we go. We're gonna make that replacement there, and then du by d theta will equal the cosine of theta. And now I'm gonna solve for d theta. So this is gonna be du over the cosine of theta is equal to d theta. Wonderful. So now I can go back up to my expression here. So this will be the integral from pi over 6 to pi over 2. Cosine of theta in the numerator. This is u cubed in the denominator, because remember I'm making that substitution. I'm letting u be equal to sine of theta. And then my d theta is now going to be du over the cosine of theta. Well, that's very convenient because the cosines will cancel. So now I'm left with the integral of pi over 6 up to pi over 2 of u to the negative 3 du. Now, that, okay, is going to end up being, when I take the integral of that, that's going to be u, whoops, sorry, u to the negative 2, because remember I'm increasing the exponent by 1. Okay, so u to the negative 2 divided by negative 2. This time, because it's an indefinite integral though, sorry, because this is a definite integral, my mistake, sorry, it's a definite integral, remember I don't have to put the plus c here. Now I know some people are going to want to put the plus c, and that's totally fine. Hey, whatever makes you happy there, but it's not necessary. Okay, so now what I've got here is I'm going to evaluate this between pi over 6 and pi over 2. But I'm going to run into a little bit of difficulty here because pi over 2 and pi over 6 are values of theta, not u. So what I'm going to have to do here is I'm actually going to have to go back and substitute u back in, the sine of theta, which is not a big surprise there. I mean, we've done that before. So this is going to end up being the sine of theta to the negative 2 over negative 2, evaluated between pi over 6 and up to pi over 2. Whoops, sorry, can't see that. Sorry. So now, what is this going to look like? Well, this is going to be, well, let's pull this out here. This is going to be negative 1/2, and then this is going to be 1 over the sine squared of pi over 2 minus 1 over sine squared of pi over 6. Now, is there, oh, yeah, you can still see that. Good. Okay. So that's what that's going to look like. I just took the negative 1/2 out because it's going to be part of the whole thing. So now, let's evaluate. And this should be no problem. Everybody knows what this is. Sine of pi over 2 is going to be 1 squared is just 1. Awesome. Okay, sine of pi over 6. Sine of pi over 6. And I can hear the groans. Okay, but sine of pi over 6, that's 30 degrees. It's going to be 1/2. 1/2 squared. It's 1/4. So it's going to be 1 over 1/4. So we're getting close here. This is going to be negative 1/2. 1 minus 4. Well, 1 minus 4 is 3. Okay, I know. Sometimes that's the hard part of the problem there, that little bit of subtraction. That's going to be negative 1/2 of 3, of negative 3, I should say, negative 3. So the answer would be 3 over 2. Okay, that's the final answer that we're going to get to. Actually, I tell you what, I am going to do this particular question in 2 different ways here. I got a little bit of room on the paper here. Let me show you another way that you could have approached this problem and still gotten the exact same results here. What I just did with you guys right here, although it works here, this is not the way I would normally go about doing this problem. Okay, here's what I would do. I go back up to my substitution, u is equal to the sine of theta, and I'm going to make my substitution, but it's about right here that I would start to do things a little bit differently. I'll just do a bit of a parallel here. I would end up getting u to the negative 3, okay, du for sure, but what I would do here is I would use my substitution here to actually change my limits. Okay, I'm going to take my upper limit and I'm going to plug this in. Okay, so when theta is equal to pi over 2, u is the sine of pi over 2. So the sine of pi over 2 is going to be 1. So my upper limit here becomes 1. I take my pi over 6. That's a value of theta. So sine of theta, my lower limit here is going to be u is equal to the sine of pi over 6. Well, I know that that's equal to 1/2 here. So what I would do is I would make a complete transition over to this new variable u. Okay? So I don't have to go back. I change not only all of the thetas to u's here, but I change my limits to values with respect to u, not theta. So now I'm still going to get, when I take the antiderivative here, I'm still going to get u to the negative 2 over negative 2. But this time that's going to be evaluated between 1/2 and 1. Okay. There's still that common factor of 1 over negative 2, or negative 1/2. But this will now be 1 over 1 squared minus 1 over 1/2 squared. Whoops. Sorry. But now if you think about that, notice that that is exactly what happened right down here. I'm getting exactly the same thing, but I'm kind of sidestepping some of the trig by doing that. And you will ultimately get 3 over 2, exactly like we did when we did it the other way. So now you don't have to, again, you don't have to do it like this, as long as if you're going to leave the limits the way they are, then you need to substitute back in that original expression. But if you're comfortable doing this, then when you make your substitution and change things over to u, change your limits as well. And you're going to use the exact same function that you set up over here to make your substitution to change the limits. Okay, let's take a look at one more question. Okay, and in this case right here, when I do this, I am going to change the limits. Okay, because I want you to see another example of that. I think the other method where you leave the limits the way they are, substitute back in, and then evaluate it is pretty straightforward, because it's basically like we've been doing integrals up to this point. It is a little bit of a different idea to change your limits here, so I want to show you that again. This one there's nothing really special going on here. Again, I've got a composition of functions here, and my inner function here is this x to the 5th plus 1. So I'm going to make that substitution here. But I want to change my differential so that I am taking the antiderivative with respect to u. So du by dx is going to equal 5x to the 4th. Well, I love that, because I can see right now a connection there, and that's going to cancel. I will solve for dx. So du over 5x to the 4th is dx. Now I can make my substitution into here. This will be x to the 4th, u to the 5th, du over 5x to the 4th. Okay, my x to the 4th will cancel, but before I get to that, I'm actually going to change my limits. So if I plug 1 in, 1 to the 5th is 1, plus 1 is 2, so my upper limit will be 2. If I plug 0 in, 0 to the 5th is 0, plus 1 is 1, so my lower limit is 1. So now my x to the 4th over x to the 4th becomes 1. I've got this 1/5 there. I'm going to pull that out. And so now I'm going to take the integral from 1 to 2 of u to the 5th du. And I'm super happy with that, okay, because I don't have to go back now to x. I can complete this function with u. I've made a complete transition over. So this is going to be 1/5 u to the 6th over 6, and we're going to evaluate that between 1 and 2. So this is actually going to end up being, what have we got here? This is going to be 1 over 30, and that'll be 2 to the 6 minus 1 to the 6. Whoops, and you can't see that. Boy, I'm doing that a lot. Okay, so 2 to the 6. Well, let's just do it like this. This will be over 30 here. 2 to the 6. What is that? 64. And 1 to the 6 is just 1. So 63 over 30. Wonderful. Except if you left it like that, I would dock you. You know I would dock you for that. There is an obvious simplification that's going to happen here. Numerator and denominator are both divisible by 3. So that would be 21 over 10. That's the way I'd like you to write that answer. Okay? So, anyway, the idea behind substitution, again, is when you can see a composition of functions there. You're going to replace that inside function with the letter u, and then you're going to take once you've established that relationship, you take the derivative of that, okay? You take the derivative of that so that you can replace the differential in the integral here. You need to do that so that you're now taking the integral with respect to u and not x anymore. Now, and hopefully that should, when you do those two substitutions there, when you substitute in u for that little expression, and then when you substitute in the du for the dx here, that should make this a much easier integral to solve. If it doesn't, then maybe you've let u be the wrong thing. You need to change what it is that you're letting u be equal to. Okay. Anyway, I hope that makes sense. When you're working with your definite integrals, remember that if you don't change your limits, okay, then you need to substitute back in the original expression for u. You need to go back to the original independent variable before you plug in your limits. But if you change your limits, then you're fine. Okay, you're fine at the end there. I hope that helps.